Hi everyone, I'm Andrew Searle from IO Industries. Just want to say thank you very much for taking the time to listen into this presentation. I look forward to giving you a good review of the new REDWOOD camera series that we have, and we'll dive right into it right now. So the outline of the presentation, I'm going to first give a background of the company, and then we'll go through the entire suite of specifications and features for the REDWOOD camera series. Talk about some new models that are coming soon that haven't been announced yet, and then go through some of the application examples where we see these cameras having a good fit. So for those of you who aren't aware of IO Industries, the company was established in 1991 in London, Ontario, Canada, and we initially developed PC-based image capture and processing software for the medical, scientific, and defense-related research areas. From 1998 onwards, we've been designing specialized digital video recorders capable of recording long sequences of high-bandwidth, uncompressed video using a really innovative direct-to-disc recording technology. In 2011, we started to produce our own series of high-speed, high-resolution video cameras. These were industrial-style cameras designed for use in computer vision applications, but as well, combined with our DVRs, they could be used for multi-camera video recording systems. Fast forward to 2019, and we introduced the VoluCam camera. This was a first-of-its-kind, multi-format video camera with internal uncompressed recording. So it was a combination of our existing strengths from our DVR background as well as our camera technology. And it was designed for use in volumetric video capture studios, as well as other synchronized multi-camera recording applications. So at a high level, with IO Industries, we produce video cameras, digital video recorders, and DVR software to go along with it. As of today, we have 20 employees. We have all in-house design and manufacturing. And we're still based in London, Ontario, and everything's under one roof. All our electrical and mechanical product design, firmware development, PC software development, our electronic test and final assembly, quality assurance, and technical support. We have active customers in over 25 countries around the world, and the main application areas that we get into include aerospace and defense testing, AR/VR content generation, scientific research, industrial machine vision, live event broadcasting, and several other applications. Here's just a quick cross-section of some of the customers that we supply solutions to across the research, aerospace, and defense markets. And for more into the entertainment-related fields, such as AR and VR content generation and live sports broadcasting, here's another example set of some of the different groups that we work with. As I mentioned before, in 2011, we started introducing a series of cameras. So these were what we call the Flare camera series. And we evolved this series over the years past that, introducing other models as well. But the general capabilities of the Flare series are to be high-resolution video cameras. They all had fast global shutter CMOS sensors and very fast digital streaming outputs, such as camera link, COAXPRESS, or 3G SDI. For those unfamiliar with these types of cameras, these had interchangeable lens mounts so that they could have an adjustable field of view. And they were all rugged with all metal designs and intended to be used in a wide variety of environments. We saw a wide application use of these cameras across machine vision, slow motion capturing, scientific imaging, live sports broadcasting, and it got us into working in the VR and AR space as well. So the types of capabilities in this range are into the 2 megapixel, 4 megapixel range at the low end, moving up to 12 megapixel and 48 megapixels at the very high end. So these were our very high-speed sensors that we work with, and they're capable, with window sizes going down, of increasing the frame rate to over 1,000 frames per second at smaller resolutions. After the Flare series, we introduced a new family we call the VICTOREM family. These were designed to be compact, physically smaller. We adopted a whole family of Sony and G-pixel CMOS image sensors. Again, sticking with fast streaming outputs such as COAXPRESS and 3G or 12G SDI. There was over 10 different sensors to choose from, spanning a range of under 1 megapixel to just over 26 megapixels, and with frame rates into the hundreds of frames per second. So not quite so fast as far as frame rates go compared to the Flare series, but generally these cameras will offer superior image quality and higher dynamic range and a lower noise level, even in lower light conditions. VoluCam cameras, as I mentioned before, are compact and multi-format variable frame rate cameras with internal recording to SSD. So these had the same sensor family basically as the VICTOREM series, so the same Sony and G-Pixel sensors, but with an internal SSD up to 2 terabytes, where we can record continuously without dropping any frames. And then the cameras have a 10 gigabit Ethernet port to download the files afterwards. So it's quite the high performance capable camera, especially for multi-camera synchronized applications. Again, with our DVR-Express video recorders, these are purpose-built for uncompressed recording at high speeds from a variety of different types of cameras. They're multi-channel, they use solid-state discs for recording, they're very precise with time stamping, and they're really unique in the market for what they can achieve. They can be PC connected or standalone devices, and they're capable of sustaining the very fast rates that today's very fast video interfaces can deliver. So moving on to what we're talking about today, with regards to looking at our camera series, we were finding that despite our existing camera options spanning a very wide range, we found customers were interested in cameras that had higher resolution as well as with faster frame rates. Just to put a point on the metric, we had this the Flare 48 megapixel camera. This is a 48 megapixel, 30 frames per second camera. And we were consistently being asked for solutions that could allow that type of resolution, but also at faster frame rates. So that was definitely the area that we wanted to start looking into as we investigated, what to make for our next generation camera. And that's what led us to the REDWOOD camera series that we're talking about today. So what we did is we selected 2 different sensors, and they both offer very similar capabilities. They both have very high resolution, low noise, and fast frame rate. So the 2 models that we'll be discussing are the 447 X52 camera and the 654 G71 camera. So the first uses the ON Semiconductor XGS 45000 sensor. It's an 8192 by 5468 sensor. That's 44.7 megapixels. And the other uses the G-Pixel GMAX 3265, which is a 9344 by 7000 sensor, so 65.4 megapixels. They both use the same pixel size, 3.2 by 3.2 microns. So the 45 megapixel is approximately the Super 35 format, and the 35 millimeter full frame is what the G-Pixel would have. The 45 megapixel has up to 52 frames per second, and the 65 has up to 71 frames per second. They both use a global shutter exposure capability. The noise, the full well charge, the dynamic range is all very similar. So you're really looking at the differences in overall resolution and frame rate capabilities that these sensors can offer. If you look at the sensor size comparisons here, the blue rectangle is the GMAX 3265, and the red rectangle is the XGS 45000. You can also see a dotted green rectangle. So that's the 35 millimeter full frame sensor size. So you can see that both are fitting within that full frame sensor size. And that's going to make it very easy to select from available lenses. In comparison, the CMV 20000 and the CMV 50000, both very popular high resolution sensors up until now, the CMV 50000 being the one in our Flare 48 megapixel camera. Those are both slightly larger than the 35 millimeter full frame format. And so you can imagine there's a little bit more of a challenging case for finding the appropriate types of lenses that can cover the sensor fully. So with the new sensors, they're both comfortably within that 35 millimeter full frame size. The XGS 45000 is a lot closer to the CMV 12000. If you can compare there, you can see this rectangle there as well. So you can compare that you're getting almost 4 times the resolution with only slightly larger image format than the CMV 12000. So the 3.2 micron pixel size introduces some new challenges, and it definitely pushes the limits of lens capabilities. The pixels are front-side illuminated type, FSI. This is in contrast to what else is out there today. Some other sensors are now using the backside illuminated or BSI type. So a small size front-side illuminated pixel is often challenged by sensitivity and fill factor because of course you have to direct the light rays to the photodiode, and there's often all sorts of other circuitry involved in the front-side illuminated architecture. The solution here is what has been done is to implement a double micro lens or a light pipe, and you can see that in the diagram here. And that's definitely made an improvement with regards to the fill factor overall. So you're decreasing your area, you're going down to a smaller 3.2 micron pixel from maybe a sensor that you've used before, but there is some consideration for that and some advanced optical technology to help still maximize the fill factor and still give good sensitivity levels. If you can compare the spectral response between the two sensors, XGS 45000 on the left and the G-Pixel GMAX 3265 on the right, they're fairly similar. You can see that the XGS 45000, it seems to have a little bit better color separation and a little bit higher red or near infrared response. But generally speaking, you're looking at fairly similar sensitivity between the two. Now, when we supply it as a color camera, we also include an IR cut filter. So you can see that the cut filter will start to decrease, of course, the sensitivity beyond about 670 nanometers. So to the left of that area is really what the you're going to be noticing for general sensitivity. So in terms of mechanical specifications, the camera body is designed to have a 62 by 62 front cross section. It has a 154.7 millimeter depth if you include the F-mount version of the camera. The reason we designed the camera in this sort of shape and form factor was to meet a few different competing demands. It helps to have the overall diameter of the camera body fit within as small of a potential enclosure as possible. With the design that we have, you have a minimum diameter of about 88 millimeters for some sort of environmental enclosure for this camera to go into. If you compare with some other cameras, even our own with an 80 by 80 millimeter front cross section, that goes up to an 125 millimeter diameter, and that could be even greater if you had side exit or bottom exit connections. So we definitely wanted to optimize the camera design so it would fit within smaller environmental enclosures. As well, the small front cross section, of course, also helps with close interocular spacing. We've had a number of customers use our cameras in pairs for stereoscopic imaging as well as camera arrays. So this is something which is also very important to maintain is, as small as possible separation, side by side between pairs of cameras. The weight is just 715 grams with the F-mount. It has an anodized aluminum case. We have multiple M4 by 0.7 mounting points on all sides. We've got tripod mounting points on the top and the bottom. You can see that there is an integrated top heatsink. So unlike other cameras where there's an additional heatsink that must be attached sort of outside the envelope of the body, ours is sort of within the overall dimensions of the camera. It's also incorporating an adjustable speed cooling fan. And we've tested it to be capable of operating anywhere from a -10 to a +50 C environment. And again, this is kind of like our other cameras, it's kind of based on assuming that there's no forced airflow in addition to what the cooling fan's giving, or any significant conductive cooling, by mounting the camera to a metal surface or anything like that. So really depending on the environment that the camera gets used and how it's affixed to a surface, the operating temperature can definitely change. So and allow for a broader range is what I mean. So it's definitely something to consider as far as how it gets integrated and used in an overall environment. As far as optomechanical capabilities, as I mentioned before, the color cameras include an IR cut filter. It's positioned in front of the sensor behind the lens mount. This can optionally be removed, or other optical filters could be installed if necessary. It's an interchangeable lens mount. It's fairly easy to interchange between different lens mount options that we have. We offer an M52 by 0.75 threaded mount with a fairly short flange distance, about 18 to 19 millimeters. We offer a Nikon F mount, which is suitable for a wide range of industrial lenses. It also includes back focus adjustment, so that you can adjust the back focus to compensate for any type of filtering that may be installed in the optical path, as well as if there's any sort of calibration needed due to lens tolerances and things like this. You can really adjust for any sort of mechanical tolerances in that regard. And as well, we also offer, like with our other cameras, the active Canon EF mount option. With this, it requires the camera to be powered through an AC power adapter. But with this adapter, it really opens up the different types of lenses you can attach. And it also gives you remote control of focus and aperture for those types of lenses. So from far away, you can be adjusting the focus, and you can also be opening and closing the aperture on the lens. And that can be really helpful in a lot of applications where you don't have physical access to the camera. So there's two ways to power the camera. You can supply power through the Power over COAXPRESS interface. Just as a note, this requires a dual link connection at a minimum, or you can supply a 12-volt DC source directly. Consumption is approximately 13.5 watts through power over COAXPRESS. That's why 2 different connections are needed. It's a 13-watt limit for each connection, and that's why we want to have 2 connections made. And it's 12 watts if you do a direct, so it's just a difference between the voltages, and the power over COAXPRESS consumes a bit more because it's at a 24-volt level. And yeah, direct supply is required if you're going to use the active EF lens mount. So we have 2 different universal adapters. One just simply supplies power, and the other, you can see on the right, also has a breakout to 2 different BNC female connectors to expose the TTL input and output ports that are on the same connector as the power. So this camera has a COAXPRESS output. Like many of our other cameras, we support either single, dual, or quad link configurations. So you can have anywhere from 1, 2, or 4 different cables coming out of the camera, depending on the type of throughput that you need, as far as frame rate, bit depth, and overall bandwidth that needs to come out of the camera. The link speeds that are supported are anywhere between 3 gigabits per second and the new 12.5 gigabits per second that are supported under COAXPRESS specification version 2.0. So by having the ability to switch between single, dual, or quad link, and anywhere from 3 gigabits to 12 gigabits per second for the link speed, you really have a lot of flexibility to move around between your data rate, your cable count, and your cable length, because your cable length is actually affected directly by the link speed. So then it's a question of how many frames per second you need or what the bit rate is, and then maybe then it'll tell you, well, at a certain bit rate I can choose to just use 2 cables, or I could use 4 at a lower bit rate. So those are the kinds of considerations that you can make. It uses the HD BNC connectors, also known as micro BNC. It's a rugged connector. You can use straight or right angle connections as far as what the cables can have on them. It's fairly easy to source the cables or even make your own with the proper crimping tools. On the back, there's also a 6-pin Hirose connector. This is your DC input, and then the TTL trigger I/O, as well as an additional 6-pin Hirose connector, and this is for connecting to the active EF mount. At the bottom left, you can also see there on the diagram just the comparison between the size of a standard BNC, the DIN 1.0 2.3 connector, which was also popular for COAXPRESS cameras, and then the HD or high-density BNC just to the right of that. So moving on to the camera features. So this is going through then all the different capabilities and functions that we put into the camera. First of all, how to configure and operate the camera. Number 1, you can do GeniCam-based control, so the REDWOOD cameras are fully GeniCam compliant. You can access all the functions that you need to through the GeniCam API. And of course, just for a frame grabber-based connection approach, just look through the documentation of the Frame Grabbers SDK to show you how to do that. The other approach is register access. So you can just bypass GeniCam if you wish and go right to the low-level register controls. All the registers are fully documented within the user's manual to let you do that. Another option is to use our REDWOOD software. So we publish a software control tool. It provides a bit better of a user interface for configuring the camera's settings. It uses GenTL, so we can navigate through different GenTL producers to access the camera, whether this is being connected through a frame grabber or connected through another type of device. The software also provides some features that are unavailable through the normal GeniCam controls, such as loading LUT files. We also supply a firmware updater utility in this software package, and that's for loading firmware updates into the cameras. And this is available for the Windows OS. Lastly is the CoreView integrated control. So if you happen to use the REDWOOD cameras with one of our DVR Express Core recorders, we've fully integrated these camera controls in the same user interface as the separate control program directly into the CoreView DVR software, just to make it that much easier to control our cameras from within the CoreView interface. The REDWOOD cameras support multiple pixel formats. You'll see that you can choose between a 10 and 12-bit ADC mode for each sensor, and then from there you can choose whether you're outputting 8, 10, or 12-bit output pixel formats. Essentially, comparing between the 12-bit and 10-bit ADC modes, On either sensor, the 12-bit ADC mode provides the lowest noise and the highest dynamic range, whether you choose 8, 10, or 12 bits coming out. The 10-bit ADC modes are more so for maximizing the frame rates, and you'll see in a couple slides the impact that that has depending on the different sensors that's chosen. Analog and digital gain controls. These are separate gain controls in these cameras. In some of our other cameras, that's the same way, such as our Flare series, whereas with the VICTOREM cameras, it was a continuous single gain control, which ramped between analog and then digital gain. In this camera, it's more going back to what the Flare cameras had, where you have a separate analog gain control, and then you have a digital gain control in addition to that. So for the XGS, it's a coarse adjustment anywhere from 1x, 2x, or 4x. And with the GMAX 3265, it's anywhere from 0.6x to 4.6x in steps of 0.2x, okay? So the reason it's offered in less than 1x is just that you can have some situations where, depending on the lighting conditions you need, you might want to change what the native, analog gain is of the sensor. It just might be the case that you won't be able to saturate, at the full pixel level if you use that. So it's an interesting capability to let you bracket the dynamic range of the sensor into certain light levels that you're going to be imaging. The digital gain control is the same regardless of the camera, and it's anywhere from 1x to 4x in addition to whatever analog gain is being applied. And you get 1,024 steps, so it's a fairly fine adjustment. So you have a lot more finer control over adjusting the digital gain than you do over the analog gain. So we have multiple exposure control modes. These let us adjust how the camera creates each exposure. And you'll see that these settings and these options are very similar to what we offered with the Flare camera family as well. So the first is free run with programmable exposure. So basically the user specifies the frame rate and the exposure time in microseconds. Again, going a little bit different from how the Sony sensors in the VICTOREM family worked, where you were adjusting exposure time in line times at the low level, and so you had a little bit less granularity to adjust the exposure time in microseconds. In this case, you're actually setting it in microseconds natively. So the XGS 45,000 and the GMAX 3265, they both have fairly short minimum exposure times, as low as 12 microseconds. And this is quite fast in comparison to the other cameras that we offer in both the Flare and the VICTOREM family. The other options are edge-triggered programmable exposure. This is where exposure will start after a trigger edge is received, and this could be coming in through a TTL connection or through the COAXPRESS interface. So essentially the camera will wait until it receives a trigger pulse, and then it will then start an exposure for a predefined amount of time that you set in microseconds. Number 3 is edge-triggered level-controlled exposure, same as option number 2, except the trigger's active time is what controls the exposure time. So this is useful if you want to have an externally controlled multi-exposure sequence. We've had people that'll sort of provide the cameras with a pulse train that has varying high times in sequence. It'll create multiple frames that each have different length exposure times. And lastly is the edge-triggered double exposure mode. And this is a special mode that's primarily for people doing particle imaging velocimetry, or PIV, which is a popular imaging technique in fluid dynamics research. Generally, your scene will be illuminated by fast laser pulses that are synchronized with the exposures. And what happens is each trigger that's sent to the camera generates a pair of images where the interframe time, or the time between the end of the first exposure and the start of the second exposure, is internally minimized by the camera's timing to be as short as possible. Much shorter than if you were to have to try and send 2 successive trigger pulses to the camera to create 2 separate exposures. The double exposure mode essentially takes 1 trigger, creates 2 images with as short as possible of an interframe time. And with these cameras, the interframe time can be very short. This is the shortest that any of our cameras have been able to offer, especially at these high resolutions, as low as 1 microsecond. So this is really going to be interesting for some people that are doing this type of imaging research. So here's a breakdown of how the frame rates speed up as you change the CXP connections, as well as the windowing, the region of interest, or ROI. So for the 447x52, the maximum resolution is 8192 by 5468. And you can see with the 10-bit ADC mode, 8-bit output, or 10-bit output, we can achieve a maximum of 52 frames per second, and that's through the 4x CXP12 connection. We can also get 52 frames per second in 8-bit through a 4x CXP6 connection. It's when we start to use the 12-bit ADC mode where we're starting to see the advantage of the 4x CXP12 interface. It does drop the frame rate down. We can no longer get 52 frames a second. It's now down to 47 frames a second, but we can achieve that now at up to 12 bits precision. So yeah, these charts are on the data sheets. It's helpful to review them and be able to see, some of the choices that you could make between the CXP connections, which again define your number of cables as well as the bit rate on the cable. And the bit rate, again, that defines sort of your cable length for a given length of cable. And then just be able to choose between, again, the 10-bit or the 12-bit ADC modes, depending on, the overall frame rates that you need to achieve. With this sensor, the maximum 1-to-1 aspect ratio resolution would be 5440 by 5440. And you can see that the frame rates over here are fairly similar to what they are at the maximum. But you don't require as fast of a COAXPRESS connection, maybe just a dual channel CXP12 to reach the same as what you'd get if you had the full 4-channel CXP12. And lastly, for the 8K Ultra HD TV2 standard, again, this is a resolution that's 4 times greater than 4K. This camera and this sensor is capable of 60 frames per second at that resolution. And that's definitely going to be of interest to some people who are doing some more video-targeted applications. This sensor, is definitely capable of those speeds, and it's able to produce that with up to 12-bit precision. When we switch now to the 654G71, you can see, again, right away you've got a higher maximum resolution, and at that high resolution we can achieve up to 71 frames per second using the quad CXP12 connection with an 8-bit output. But when we switch to the 12-bit ADC mode, again to get the better dynamic range and the lower noise, the frame rates that the sensor can offer drop quite a lot. The maximum frame rate at this resolution is then gone down from 71 to 31 frames per second. So it's definitely going to be a question, depending on your application, whether you'll need to use the 12-bit ADC mode for the maximum image quality or the 10-bit ADC mode for the maximum frame rate. In this camera, the maximum 1-to-1 aspect ratio resolution is about 7,000 by 7,000, and you can see it's very similar frame rate capability to what was used at the full resolution. But again, as you decrease some of the connection speeds, you can still get fairly good frame rates with that. And then in comparison, for the 8K resolution, we're over 100 frames a second with this sensor in the 10-bit mode. However, in the better image quality 12-bit mode, we're only able to meet 51 frames per second. So most cases, if it was going to be an application just needing the 8K resolution, it's likely the case that the 45 megapixel camera would be a good selection for that. That being said, if anybody needs more than 100 frames per second at the 8K resolution, then it's really it's going to use this sensor instead. Both cameras support multiple regions of interest. You can have up to 16 non-overlapping windows. It has to be the same width for each window, but you can have unique coordinates and height for each window thereafter. So you can see, you can define where these windows are within the full sensor field of view. They just can't overlap. That's vertically. They can't have essentially any shared rows. They turn into sort of a composite image when it comes out. So you can see how with the 10 separate selections, it turns into a single frame on the output. So it's really useful if you have a predefined area of this field of view where you can focus your interest, and then you can, again, speed up your frame rate of the camera for any of the rows that you're skipping, essentially. That'll help to speed up the overall possible frame rate, and then it decreases the data that's coming out of the camera as well, which, again, then helps to save some of the processing time down the line. Some of the other features include auto exposure control. Auto exposure control, of course, is to adjust either your exposure time, your digital gain, or your aperture as the scene levels change. You can choose pretty much any of those three, and you can define what the range would be that you would allow each of them to cycle forward and backward in. You can choose to auto adjust based on the levels that full image shows, or just within a user-defined zone within the frame. So, for example, if you're looking at a horizon and a sky ground type situation, you could exclude the sky from the auto exposure calculation and just make sure that this area that's seen for the ground is just always perfectly auto exposed because the sky would be so much more bright. You can choose to adjust the response speed as well as the target value for the auto exposure as well. The sensor black level adjustment it's a sensor-based offset, so it can calibrate the dark levels to be true black by subtracting a certain amount from the base level. Typically, our factory calibrated value is what you're going to end up using, but you can manually adjust this or perform a recalibration yourself. There is a color balance feature for the color models, and what this does is apply gain to the individual channels in order to calibrate the white level to true white. This is applied on the raw pixel data, so the red gain applies to just the red pixels in the raw output, green gain applies to just the green pixels, etc. This can either be done in a manual way with you just user adjusting these three gains, or you can do a one-shot auto color balance. You can also have tracking color balance enabled, which is a continuous auto adjustment. It basically adjusts as the color temperature of the scene changes, let's say from a sunny day to a cloudy day. And you can also change the response speed as well. And lastly, there's a black balance on the color models as well. It's similar where there's a red, green, and blue offset to either add or subtract to the pixel levels. And this helps to calibrate the dark levels per channel to a true black. This can either be done manually or it can be a tracking continuous operation as well. There's also user programmable lookup tables, or LUTs. These are used to apply gamma or EOTF corrections or other nonlinear gain conversions to the pixel data. You can use these to adjust contrast or compress dynamic range. The camera can store up to 8 separate 12-bit LUTs within the camera. We include a big selection of different ones for different gamma. You can also create your own custom lookup tables, and then you use the REDWOOD control software to load those into the cameras. We have horizontal and vertical image flipping built in. This can either be X, Y flipping, or also X plus Y, which is the same as 180-degree rotation. So if you've mounted the camera upside down for any reason, you can enable this in the camera and it'll output the images appropriately. There's built-in image corrections such as pixel replacement, fixed pattern noise correction, and flat field correction. And we also have some enhancement features new for this series, which include a denoising filter and a detail enhancement filter. So just a quick step away to talk about high dynamic range imaging. Just in general, with all types of cameras, a given image sensor is going to have a native dynamic range, and it can often be far below the dynamic range of any scene that it's being used to take a picture of. So one approach to capture more dynamic range is to take several images, basically shot at different levels, and then recombine them into a single HDR image using a technique called image fusion. Now, this approach works well for stationary scenes, as you can see in the example below. But because you're taking multiple successive exposures over time, anything that's moving throughout that time when you're taking those individual images is going to cause artifacts in the image fusion algorithms thereafter. So industrial image sensors will often have features to extend the dynamic range of the sensor by allowing multiple exposures to be captured within a single frame period. So instead of having to capture successive images at different levels and then combine them, there's these neat features to capture within a single frame period, so you're reducing the amount of motion that could possibly be causing artifacts. Now, one approach that's used in some of our cameras, our flare cameras, is a per pixel exposure reset. This is a neat point feature, and we call it the piecewise HDR feature in those cameras. Now, this approach has benefits because it's a per pixel feature. It's kind of, you can have areas of this of your frame that are affected by the need point, but other areas that aren't. But in general, this can still have motion artifacts because it's still a multi-exposure type HDR approach. It's essentially resetting the pixels and restarting their exposure at different points within the typical frame exposure period. It's also got noise-related side effects, at least with the sensors that we used in the past. Enabling this basically eliminated the advantage of the built-in correlated double sampling feature, which got rid of a lot of the pixel noise. It also is something that's primarily a feature for monochrome sensors, and really the The color type sensors would have it as well, but it wasn't really aware of which pixels were which, essentially, which were the blue or red or green pixels. It's not aware of the color filter array. Another approach, and this is something that we do have in some of our other cameras already, is called interleaved HDR. And what this does is has alternating rows or alternating columns that have different length exposure times. So what you can do is create from one exposure period 2 images that are essentially half of the resolution in one direction, but it's captured within the same frame period. So again, it's like taking 2 successive images, but it's not going to have the same degree of motion artifact. But one of the more newer options that we're seeing, and it's until recently it's only really been available on scientific CMOS sensors, is what's called a dual gain HDR. So a single exposure creates 2 images coming out of the camera because the exposure, the pixel charge essentially, is read out through 2 different analog gain levels. So you're getting 2 different brightness levels, but it's not because one image has got a longer exposure time than the other. It's because they're going through 2 different gain paths. So this right away eliminates any motion artifacts because you're not seeing 2 different positions of a moving object within those 2 images. The downside of it really is just that it limits the maximum frame rate because you're outputting twice as many images essentially over the same period of time. So depending on the configuration of the camera, you might be limited to half of the frame rate that you had before. But again, it depends on the resolution and the sort of frame size that you're dealing with. You may not be impacted that much by it. So moving to where our cameras here are, the 45 megapixel camera has the dual gain HDR mode. So this is where it's maintaining the full resolution. We're not having odd or even columns being used or anything like that. And you can see from the diagram, your normal mode of operation, you have your standard mode, and you get to choose to expose the image for a fixed amount of exposure time, and then either have that use a low analog gain, and then maybe be optimizing to see the highlight details in the scene, or you can have it go through a high analog gain, and then you, of course, are able to see more of the shadow details. With the dual gain HDR mode, you're getting to maximize the detail in both. Okay, you've got the same exposure that's happened, and the pixels have been exposed for a fixed amount of time, and then this pixel data gets sent through 2 different analog gain levels. What the result is that the camera outputs essentially an image that's twice as tall, has twice the number of rows as a normal exposure image would have, because every other row is either the shadow detail or the highlight detail. Now, you can either have this processed in camera, or you can leave it so that it's just essentially processed after the fact on the receiver side. But you're able to recombine these 2 images and get both shadow and highlight detail together. So this is a really neat approach. Again, the maximum frame rate is going to be cut down because you're outputting twice as many rows per frame. But again, it might just be, depending on the frame rate that's needed for the scene, this can still provide quite a impressive result as far as improving the dynamic range. As for the 65 megapixel, this capability is the interleaved HDR. So this is much like some of the flare cameras that we've had. And again, it's a capability that can still serve to extend and increase the dynamic range. However, it just needs to be known that there's a chance of having some motion artifacts. So with this, it's row-based exposure. Essentially, we can do alternating odd and even rows that have different exposure times. If you can imagine, you could take one exposure at a short exposure time and be able to see the highlight detail in the scene. You could also take a longer exposure in that same scene and be able to see the shadow detail. With the interleaved HDR exposure, we've got 2 exposures happening in one frame period. So you can see here, the short exposure of the 2 lines up at the end of the long exposure. So you can see here, it's kind of like the other rows are kind of just held and not starting exposure until near the end of the other rows exposure time that's already started. The image that you get out has the same number of rows as a normal exposure image would. It's just that the odd rows have sort of the long exposure pixel data, and the even rows have the short exposure pixel data. So this means you can maintain the same frame rate that you'd normally be operating at. It's just that you have half the vertical resolution, essentially, on these individual fields or subframes, if you will. So when you're reconstituting them into an HDR image, this is something you can kind of compensate for with some interpolation, some bilinear interpolation as you're reconstituting the frame. This is a case where we can't do the image fusion in the camera in this case. This is the case where it'll always output as an unprocessed image for reprocessing kind of in separate software. And if you are using one of our video recorders, like the Core 2 recorders, we do have the feature to do the processing inside our CoreView software. But otherwise, we can provide references to some of the different utilities and different algorithms that can be used to do this processing in a post-processing application. So generally speaking, in comparison to some other industrial machine vision interfaces, we're really standing behind COAXPRESS. We think it's a very useful and feature-packed interface. We think it's great because of having the simple and inexpensive long-length cabling. Cables are fairly standard. You can get them because they're used also for the other types of video interfaces in the world, like SDI video. These coaxial cables are widely distributed and able to be found. And if you can't, then you can actually make your own. So it's not a proprietary cable. There's lots of flexibility in what kinds of cables, what length that they can be, and there's just lots of different cable options as opposed to some other interfaces where you're locked down with short lengths and specially molded cable heads and stuff like that. So cabling is really the main driver for advantage on the CoAXPRESS side. But it's also, in comparison to some other interfaces, just a lot more reliable for transmissions. We have this point-to-point connection. It's very deterministic. There's really no chance for data to be lost. And it's also very deterministic timing. So having it go into a frame grabber, in a real-time application, you can get very reliable timing for the frame and be able to use that for machine control and robotics and things like that. Along the same lines, in that you're using a frame grabber, these frame grabbers will typically have robust I/O for interfacing with the outside world, either to synchronize the exposures or to control robotics or machines nearby. So that's a definite advantage of using a frame grabber in comparison to cameras that are using more IT interfaces like Ethernet or USB or those types of interfaces where you're connecting it to a computer, so you don't quite have the same advantages that if you had plugged it into a frame grabber. And in general, I mean, CoAXPRESS has evolved a lot over the last 10 years. There's a broad ecosystem of supporting equipment out there now. Of course, there's the cables, there's cable extenders if you need to repeat the signal, there's fiber extenders if you want to go very, very far distances, and there's a broad range of frame grabber vendors that have lots of options for CoAXPRESS frame grabbers. As well, if recording is needed, of course, we have our uncompressed video recorders, the DVR Express Core series, and we'd be happy to share what the right model would be to match with the capabilities of a given camera. With that being said, we are developing something kind of interesting here, which is a new series of the REDWOOD cameras that use an optical interface, which is CoAXPRESS over fiber. We've had applications where cameras need to be positioned really far away, and there is the market to choose from a couple different fiber optic extenders for CoAXPRESS signals. But for those really long distance applications, it's sometimes undesirable to have those extra components, the extenders and the different cable stubs, in order to get the signals very far. And not just our customers found this, it's something that people have seen around the world. And as such, there's been an effort to put a new revision together of the CoAXPRESS interface, which will extend the protocol to use fiber optic connections and not just coaxial connections. So this is something that's underway. It's not fully complete yet, but we're working on our designs for the cameras. There's already some frame grabbers out there right now. You can see a Eurosys model that is supporting this CoAXPRESS over fiber, early adoption phase type approach. We're expecting to make an announcement roughly in the second quarter of this year with more information about our models and their capabilities and that kind of thing, but it's just something to be aware of. It's also one of the reasons for the camera's shape. Of course, you're going to see that the shape is going to be maintained. We're not changing the shape or anything, but now we'll be able to insert that pluggable transceiver in the back. And that's also some of the reason for the length of the camera design. So that's something to be aware of. And if you have more questions about that, we can answer those, of course. But it's something new that we think will be pretty interesting for some long distance imaging applications. I just wanted to point out, another camera that's available right now. We announced it just in December. We call it our 8K SDI camera. Similar but different camera to the REDWOOD series. It uses the XGS 45000 sensor, but instead of a COAXPRESS output, it uses a quad 12G SDI output. Now this gives us 8K video at up to 60 frames per second, and we're outputting color video. Okay, this is color standardized format video. It's intended for applications that need, video sent directly into a display or directly into, a live broadcast infrastructure. That's what people use the SDI interface for. So it's something to be aware of if you're interested in these Redwood cameras for the purpose of 8K related video applications. You might find that the 8K SDI is also an interesting option to consider. And we're going to be having another webinar soon that's going to cover this model in more detail. So stay tuned to know more about that. So I just wanted to review some of the applications that we think that the Redwood cameras are going to be helpful for. And it goes along the lines of some of the existing applications that we see our cameras used in. And again, many of those are also asking for higher resolutions and higher frame rates, and that's where the Redwood will fit quite well. So high performance machine vision, this is where we're not talking about barcode scanning on bottles or anything like this. It's really the areas that need these very high resolution, fast frame rate cameras, such as in electronics manufacturing for automated optical inspection or solder paste inspection, any kind of surface inspection tasks with large surface areas. You can replace multiple smaller cameras with a much higher resolution individual camera, and LCD inspection. Again, the greater density of LCD panels and the higher resolutions of them are just demanding higher and higher resolution and higher frame rate machine vision cameras. Multi-camera motion capture, volumetric video capture, and 3D or 4D body scanning. This is a case where there's a good demand for higher resolution and these synchronized camera capabilities that the industrial cameras offer. So definitely see that there will be some need for these higher resolution 45 and 65 megapixel sensors in that area. Scientific research. Again, our cameras get used in a lot of widely ranging applications such as fluid dynamics, structural design, wind engineering, behavioral studies of different animals and insects and things like this. So definitely see some benefit of the higher resolution and frame rate for the Redwood cameras there, as well as in commercial research and development. Some automotive testing applications do require some quite high resolutions, and then some other interesting sort of resource monitoring applications as well, and remote inspection. Aerospace and defense testing, it's again a bit of a mainstay area for our cameras, and specialty live broadcasting and video production, especially that these cameras are reaching that 8K resolution capability at 60 frames per second and beyond. There's definitely going to be some interesting applications of making use of those resolutions in the live broadcasting and digital cinema type fields. As we saw with our Flare 48 megapixel camera, there was a good amount of interest in high-end surveillance and aerial mapping. And we can see the same would be true for the Redwood camera series as well. Of course, by pushing that resolution to 65 megapixels, but also by increasing the frame rate. There's lots of cases where multiple samples need to be captured, and having the ability to get a faster frame rate beyond the 30 frames per second that we could offer before is definitely going to be of advantage in that as well. So with the introduction of these new cameras, it's definitely expanding our high resolution and high frame rate options within the overall camera range. So how can you find out more? Again, please visit our website, go to the products section and the cameras section. From there, you can see the features, specifications, photos, learn all sorts of other things. You can access our data sheet, you can download the user's manual. And we also have an online frame rate calculator, which is helpful so you can determine what the maximum frame rates would be based on a given output configuration and window size. And that's everything. So there's going to be a brief poll that's going to pop up. If you wouldn't mind just answering a couple quick questions, that would help give us some feedback here. And I really appreciate you, taking the time to listen in and learn about this new series of cameras. We'd be really happy to talk with anybody else who has any direct questions. Best way to get in touch with us would be to email sales@ioindustries.com, but you can also just follow us through our social media, through LinkedIn, Twitter, and we'll be publishing a couple more webinars, as I mentioned. Pretty soon we'll do one reviewing our STI POV cameras, and then shortly after that it's going to be another one updating about the VoluCam camera series, some new features and some new models. So once again, thank you very much for your time, and I do hope that this was interesting, and we'd be very happy to talk with you more about these cameras and learn how they might fit well within your applications. Thanks again, and have yourself a great day.